I'm going to run through the sketch of the graph that we did in class on Tuesday, just to give you a perspective on the way that I approach these kinds of problems for one that you have already done yourself. And we can see the kind of efficiencies we can put into this process of curve sketching. So I want to sketch the graph of g of x. So step one, I'm going to calculate the derivative of g of x, and to do that I'm going to rewrite this as 6 times x squared plus 3 to the negative 1. That way I don't have to use the quotient rule. That's going to equal negative 6 x squared plus 3 to the negative 2 times 2x using the chain rule. So I'll rewrite that as negative 12x over x squared plus 3 squared. And I want to know when this is equal to 0 so that I can find the critical number. So I look at the numerator. The numerator will equal 0 when x is equal to 0. And the denominator, well, I look at x squared plus 3. I know that x squared plus 3 is always going to be positive. So whenever I square a positive number, and there's no way to make x squared plus 3 equal to 0, so I know the denominator can never equal 0. So I only have one critical number. So now I'm going to create a number line for my critical numbers because I want to know the slope on the left and the right. So this is going to be g prime, showing me my slope. So I think about what negative 1 will be. Well, one thing that's nice about doing this with fractions is all we care is whether or not the fraction is positive or negative. So when I plug negative 1 into the numerator, I get a positive number. When I plug negative 1 into the denominator, I'm going to get a positive number. So I know that I have a positive slope. And on the other side, when I plug 1 into the numerator, I get negative 12. When I plug 1 into the denominator, I get a positive. So I know that I have a negative slope. So let's just simplify that to positive on the left of 0, negative on the right of 0. And now I know that since my graph goes from increasing to decreasing, that 0 is a max. Let's go ahead and figure out what the y-coordinate is because we are going to graph this. So g of 0 is equal to 6 over 0 squared plus 3. That's equal to 2. So I now know that my maximum point is 0, 2. Then we're going to move on to the second derivative. And I'll start here at the first derivative. And I'm going to use quotient rule. So for my second derivative, g double prime of x, let's make u equal to negative 12x and v equal to x squared plus 3 squared. So u prime is negative 12, v prime is equal to 2, x squared plus 3 times 2x, or we'll just go ahead and make that 4x times x squared plus 3. And I'm going to leave it as x squared plus 3. Often multiplying out binomials creates some inefficiencies in problems. We'll see how that's the case in just a second. So we'll set this up, u prime v, so negative 12 times x squared plus 3 squared, minus u times v prime, so minus negative 12 is going to be plus 12x times 4x is 48x squared times x squared plus 3. Divided by, we want to square v, so x squared plus 3 cubed. Hopefully you notice here that the way we've written things out, that we have an x squared plus 3 term in all of our places. That should have been a fourth power in the denominator, not a third power. So it was originally fourth power, but we're going to knock it down to 3. So I've got negative 12 x squared plus 3 plus 48x squared over x squared plus 3 to the third power. And let's go ahead and simplify the numerator. So that's negative 12x squared plus 48x squared, so 36x squared. And negative 12 times 3 is minus 36. You could factor out that 36 if you wanted to, 36 times x squared minus 1. So let's just go ahead and do that. 36 times x squared minus 1 over x squared plus 3 cubed. Again, we want to find potential inflection points, so we want to know when this thing is equal to 0. The numerator will equal 0 when x is equal to either positive or negative 1. And the denominator, we still have x squared plus 3, where there's no number for x that will make this equal to 0. So there's nothing for the denominator. So we just have two potential inflection points. So we'll stick those on our number line, negative 1 and positive 1. And again, we're going to plug numbers into our second derivative in order to see what the concavity is for each of these. So g double prime. And again, all we care about is the numerator and denominator of the fraction. Are they positive or negative? So when we plug negative 2 in, our numerator is going to be negative 2 squared, or 4 minus 1, which is 3. Positive times 36 is still positive. And we've already established that the denominator is always going to be positive. So that makes our calculation here a little bit quicker. All we care about is the numerator and whether it's positive or negative. We can plug 0 in to the numerator. That's 0 minus 1. That's a negative 1 times 36. That's going to give us a negative number on top. And since the denominator is positive always, we have a negative concavity. And to the right of 1, we'll plug in 2. 2 squared is 4 minus 1 is 3. That's a positive on top, 3 times 36, giving us a positive concavity to the right of 1. Concavity does switch at each of these points, so they are both inflection points. So let's go ahead and figure out what those inflection points are, since we are going to graph them. Again, we're going to go back to the original function. So g of negative 1 squared is 1. So we get 6 over 4, which is 3 over 2. And g of 1 is going to produce the exact same result, because negative 1 and 1, when you square them, are the same thing. Also 3 halves. And so we have two more points, the inflection points, negative 1, 3 halves, and positive 1, 3 halves. Now, once you have done your asymptote lesson, we're going to want to just analyze this briefly with asymptotes. So we'll remind ourselves that g of x is equal to 6 over x squared plus 3. Vertical asymptotes occur when the denominator equals 0. Kind of already established that x squared plus 3 can never equal 0, so there are no vertical asymptotes. Horizontal asymptotes are based upon the limit as x approaches infinity. And in this case, since the degree of the denominator is greater, that's going to approach 0 as x approaches infinity. And so we have a horizontal asymptote at y equals 0. Oblique asymptotes occur anytime the degree in the denominator is exactly 1 greater than the degree in the numerator. That's not the case here, so we have no oblique asymptotes. So I believe we have everything we need in order to sketch our graph. Go ahead and plot our points first. We have a maximum value at 0, 2. We have inflection points at negative 1, 3 halves, and 1, 3 halves. And we have a horizontal asymptote at 0. Now this breaks the graph up into 4 sections. The first section is everything left of our first inflection point, and we want to check both the slope and concavity to the left of negative 1. Well, we have our slope here to the left of negative 1 is positive, and we here have our concavity, it's positive, and we have an asymptote that is 0, and so we're going to come up from our asymptote, positive concavity, positive slope, until we hit our inflection point. It is an inflection point, so our concavity changes at that point. However, the slope remains positive. So moving on to our maximum value, the slope continues to be positive, but now we see a concave down. Again, concavity changes, and we learned from the first derivative that the slope changes to negative. So now we are going to go down to our second inflection point, where concavity changes again, and we approach our asymptote of y equals 0. And there's a graph of 6 over x squared plus 3.